day 8. We've got some trees. So the problem itself is fairly easy to explain. So actually, I will start by doing that. So this is a grid. I thought this was a list of long numbers at first, but it's a grid. And it represents the height of some trees. 0 being the shortest and 9 being the tallest. And what we're interested in is which trees are visible from a particular vantage point. So a tree is visible if all other trees between it and the edge of the grid are shorter than it. Only consider trees in the same row or column. That is, only look up, down, left, or right. So here we can see 0. 0 is visible and 9 is visible. 3 isn't because it's less than 9, 5, 3. And then whereas from left to right, 3 is visible, 5 is visible, this one isn't visible, 9 is visible, and 0 is not visible. And our job is to essentially come up with the number of trees that are visible from all directions. That's this, etc., and then up and down as well. So given this rather interesting problem, what's the extension going to be? It's tabletop treehouse, and we want to determine whether there is enough tree cover to keep a treehouse hidden. So I guess if it's above a certain number of trees that are visible, yes. And so if we were thinking about the extension, we might imagine that they might want us to try to place the treehouse in some way. It could be that they want to find a cell that is not visible from any vantage point. I don't know, that could be it. So we might just want to keep this in mind as we write the code, and particularly in our data structures, because we kind of get to keep our data structures. The processes are probably not going to be that useful, but the data structures probably will be. So we want to make sure, I think, that we're keeping all of the data and we don't shoot ourselves in the foot. So I've had a bit of a think already on how to have this data structure, which is a grid where you can have rows and columns and left and right columns and up and down, or up and down columns and left and right rows. And I'll start by explaining that. So if we look at this, we might immediately think, and this is me being a little bit going down the path that I always go down of coming up with 2 clever ideas, but I say clever, they're not clever in the sense that they help me get anything done. They just feel clever to me. So you might think the right way to implement this is with a list of lists. So you'd have, 3, 0, 3, 7, 3, 2, 5, 5, 1, 2, etc. But how do you get the columns then? Well, you could go through and just go through and get the first item of every, or 0th item of every list, and get them that way, which will be fine. And then what do you do to get the number of trees that are visible? Well, you might think, okay, I'll go through this first item. I'll go through the rows and I'll see, is it visible left to right? Is it visible right to left? And if, you'll work out whether it's visible left to right. Okay, so in this case, we would say, this one's visible, this one's not. This one's not visible, this one's visible, this one's not visible. And then, so we've got 3, 7, and that's it. So we've got 3 and 7. So, okay, we're doing pretty well. And then here, this way, it's 3 and 7. And then none of the rest. And you're like, oh, wait. Well, those are the same. Some of those trees are the same. This is the same 7. There's only one 7 here. So actually, we've got to, we don't want to double count trees because our question is how many trees are visible from outside the grid, not how many trees in total if you were to count from every single vantage point, including duplicates. So in this case, the answer is actually within this row, the answer is actually 3, because there's this 3, there's this 7, and there's this 3. And this 3 is visible from right to left, and this 3 and this 7 are visible from left to right. So we need to not double count trees. So we need to have some way of keeping track of the trees that we've seen and not counting them twice. And more than this, we also need to count this going down and up. So we need to not double count across any of these axes. And a tree could be visible across any axis. So that's sort of a bit of a problem. I mean, it's solvable, but that's where my sort of idea comes through. And I've just had another thought. So let me just make a note of this. Let's think about that in a moment. So my idea is that we have a list of lists or rather we have a list of rows. Let's say in fact that we're dealing with like a 2 by 2. So it'd be 1, 2, 3, 4. Let's say this is let's ignore this for a moment. And this. So in this case, we could have 1, 2, 3, 4. But actually, my idea is that instead we have like a dictionary like this, and a dictionary like this, and these are the rows, and these are the columns, and these dictionaries are actually the same dictionary. So if this is the dictionary with 1, 2, 3, and 4 in, this would be 1, 3, 2, 4. But these would point to the same dictionary in memory. So when we go through, we can update. We can add to this dictionary. Let's say seen from direction index or something, and then we would be able to see when we'd seen trees multiple times, and we would also, as a bonus, we would then have an easier thing to iterate over, because we just iterate over the rows, go forward and back, iterate over the columns, go forward and back, and we don't need to worry about double counting because we can just go through and if we keep track of, let's say, all of the sightings in a list or something, then we just need to count whether it's been seen at all, and we'll keep track of where it's been sighted from. So I think this is kind of a neat idea, and it might save some work. So of course it might also really mess things up because it's not maybe the obvious solution. So that's one idea. I think that solves part of it. So another one, what if we, so going back to this thought, what if we go tree by tree? So if we look at this one, could we just go item by item and say, is this visible from up, left, down, or right? Is this visible from up, down, left, right? And we could tell this by saying, is this the highest? Is this the highest number? So let's say we're looking at this 0 here. Is it higher than any number to the left? Is it higher than any number to the right? Or is it the highest? Is it the highest of the numbers of these numbers, or these, or these numbers? And with the 7, is it the highest of these numbers or these numbers? And it is. And for this one, but let's say pick another one. Let's take this 5. Is it the highest of these numbers or these numbers? And it is here, and it's not here. Is it the highest of these numbers or these numbers? It's higher. It's the highest of these, and it's not the highest of these. Whereas this is the highest of these numbers. So that's quite nice, actually. And it would scale by, so you'd go through each item. So you'd have the number of items times okay, so this one, let's say this one, this letter here that's in, let's say this one in the middle, that'd be the average. This one requires comparison against 0 and 3, with maybe a bit of short circuiting. So that's 2 operations and 2 operations. Actually, this one will be the average of all of them, won't it? Or will this be the maximum? No, it'll be, I think let's take this one. So comparison against 2 items, comparison against 2 items, so that's 4. And then 8. So it's 8, and this is 5 by 5. So it's 5 5 by 5 is 8 operations per item. So that's 8n. And what's that in terms of the columns? It's the number of rows minus 1 plus the number of columns minus 1. So it's C plus R plus minus 2. So for this, it would be 8 times, well, CR, really. I'm sure that multiplies out to something really cool. 8 times 5 times 5, that's 200 operations. And what about for the actual input? Okay, so it's like, I'm just going to put this in the text editor to check the length. I'm not going to do any coding. 100 columns by 100 lines. So it's 100 plus 100 minus 2 times 100 times 100, which is 198 times 100 times 100. So 2 million operations. It's not so bad. Okay, well, that could be another way of working. Wait, isn't that just what I was going to do anyway? I suppose the other way of doing this is to go through for a particular, let's say 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. I think actually I want all of these to be no. There we go. So let's take this row here. We've got three, zero, 3, 7, 3. And so what we could do, if we weren't going item by item, then we would go through and we'd say, let's actually put this a little bit here. 1, 2, 3, 4, 5. Okay, so we go through from 4 index we'd say like let highest be 0 for index, or -1 actually, because 0 would still be visible from the is a is a tree of height 0 visible? Yes. Well, all the trees around the edge are visible, so yes. For index, if height is above highest, reset highest, mark tree visible. So it's this sort of algorithm, I think. Would that work? Okay, so let's run through it. Okay, with 0. And let's keep track of index. So for index 0, highest is -1. And I need a is the height above highest? In which case, yes, it is. So the highest should be 3, and this should be marked visible, which we'll do here. For ID 1, the highest is 3. Is the height above highest? No, so it's still 3. We don't do anything. Okay, 2. The highest is still 3. The highest after is well, 3. Nothing's changed. If this is 4, the highest is 3. The height is 7. Therefore, this should change. And we mark this one as visible. Okay, and for, actually I've missed one. And for 4, The highest is 7. Is 7 higher than 4? Or is 3 higher than 7? No. So highest after is 7. Great. So that works. We get 0 and 3 here. And this takes, I feel sure this must be more efficient than going through item by item. So this takes 8 it doesn't really matter, does it, Kay? Take eight operations per row, and this would be 8 comparisons rather. So this would be, well, 4 comparisons plus 4 comparisons going the other way. But this takes 8 per item, and this takes 8 per row. So this is strictly better, I think. So we should stick with the way I was thinking of doing it. We shouldn't go tree by tree, I'm pretty sure. Although it would be kind of nice to go tree by tree. It would be kind of pleasing to program that. Okay, so I think we're pretty close. Let's read through these. Top left is 5, is visible from the left and top. The top middle 5 is visible from the top and right. The top right 1 is visible from any direction, is not visible from any direction. The left middle 5 is visible, but only from the right. The center 3 is not visible. Sorry, the center 3 is not visible from any direction. The right middle 3 is visible from the right. The bottom row, the middle 5 is visible, but the 3 and 4 are not. Okay. Is this enough to solve the problem? Basically, I need my kind of main algorithm now. So, like make structure, go through rows, call mark highest row, call mark highest row reversed. I really wish there was a not in place reverse. I'm going to check that actually. Right, okay. Colon, -1. Fine, that works. Great. And it'll be a little space inefficient, but probably fine. Probably fine. I'll only be going through 200 rows and 200 columns. Go through columns. Call mark highest col. Call mark highest col reversed. This will be really messed up if Python dictionary immutable, if they're immutable. Yeah, they're mutable. That's good. And we need to have a mark. Well, and then we well, we go through go through all cells, count all that have been marked. So make structure by going through okay, well, I need to plan that out because I'm going to need 3 data structures: rows, cols, all. And then I'm going to go through, I'll go through the rows, I'll go through the columns, I'll go through all the cells. And I'll count all that have been marked, and I'm going to mark them in some way. Okay, so what do I need to plan out now? I need to plan out make structure mark highest and the cell. I'm going to make it a class, actually, make it an object. So for make structure, I'm going to go through the lines in the file, split them into characters. No, wait. Generate in rows, in calls between the characters, populate the row, populate or push onto the column, each column, and then I'm done. Oh, and actually add cell to all also. Okay. Great, so that's make structure. Mark highest is going to be this algorithm. This is going to be the main loop. And then cell is going to be in it with height mark with direction and place. It might be handy to know the place, or like coord. Well, is that really relevant? It's going to know its own coordinate if I give it that. X and Y. Or rather, col and row. Let's not get upset about coordinates again. Great. And we're going to go from column. I'm going to go through from column. Sorry, I'm still recovering from COVID. We're going to go from column 0 and row 0. No one indexing here. So I think we're good. Plan of action. To make a structure 3 Right, mark highest. Right main loop. Okay. All right, let me organize this as well. So this one, great. Make structure. Mark highest. And then main after that. And I think that puts us in a good place to get started. All right, give me one moment. Okay, I'll share VS Code. Line up my notes. Oh, I'll get the data and the trial. Okay, that's good. Great. And one more thing, if I end up with any time left over, I'm going to write a little thing to replace the thing I keep copy pasting around, the sort of file reader thing. It's very irritating doing that every time. So I'm gonna do a bit of work on that. Start building a bit of a utility library. If I have time, I might not. Okay. Let's get started. Oh gosh. Okay. Sorry, that's not a good start. Okay. All right. Don't need any tests for that, I think. This one might be different. Okay, make structure. Probably a nice way of doing that. Okay. Oh, doesn't matter. Don't need to do that. Okay, great. Fine. Anyway, I'm getting ahead of myself. I need to generate rows and columns. One, two, three, four, five. Great. Whatever. Okay, go through the lines in the file, split into characters, populate the row. So I need to say row index is 0. So this should increment at the end here. Okay, great. Okay, columns. Three, two, six, three, three, 0, 5, 5, 3, 3, 3, 5, 3, 5, 5, 7, 1, 3, 4, 9, 3, 2, 2, 9, 0. Okay, and the rows, 7, 3, and at the end, 3, 5, 3, 9, 0. Fine. Okay. Okay, but it's actually not, it can't be that. It's got to be, it can't be the actual number. It's got to be the cells. Which means I need to rethink this bit. It's going to be the column will be, ugh. Probably a nicer way of doing that. Didn't learn my mistake from yesterday. Don't need this bit. Okay, is that still right? 30373. Yes. Three, two, no. 303, okay. Let me focus down this. Okay. That's not right. Okay. 30373 to 35390, and then the calls. 32, yeah, it was right. 3263305, yeah. 32290. Great. Okay, so that is working. And then all cells. Okay. Great. That's that bit. Okay, mark highest. Column, row. Okay. Okay. That should be marked, surely. Oh, it's different from what I thought. Yeah, it is actually visible both. Yeah, okay. Fine, that works. Because it's visible from this direction and also this direction. So we should add another one in here, which is even shorter. So this one should be visible from both, and this one should be visible only from the right, which is perfect. Okay. Okay. So the main loop, our name, rows, calls, or basically size, because they're the same, which I think that's true. Oh no. 1, 99, 99, right? I'm not. Oh, okay. All right. Let me check for that at the end. Okay. Rows, calls, file name. Got you. Okay. For row in rows. Left to right, right to left, top to bottom, top. Okay. $21. Is that right? 21. Yes. I think it's 100 by 100, but I've sort of lost my. Okay, let me look at this. This says 5, column 6. Line 5, column 6. But it's got 5 rows and 5 columns. Anyway, I think it's fine. I don't think they'd do something so cruel. 1845? I mean, maybe. Could be. Should we try it? 1845? 1845. Yes. 1104. Left. So whatever that is, less difference between that and 30. Okay, now we find out if we've totally ruined our evening by not writing this in a way that needs to be extended. Okay. Content with the amount of tree cover available, the elves just need to know the best spot to build their tree house. They would like to be able to see a lot of trees. Oh, great. Thanks. To measure the viewing distance from a given tree, look up, down, left, and right from that tree. Stop if you reach an edge or I should have done it the way I thought. Or at the first tree that is the same height or taller than the tree under consideration. If the tree is right on an edge, at least one of its viewing distances will be 0. The elves don't care about distant trees taller than those found by the rules above. The proposed tree house has large eaves to keep it dry, so they wouldn't be able to see higher than the tree house anyway. In the example above, consider the middle 5 in the second row. Looking up, its view is not blocked. It can see one tree of height 3. Left, its view is blocked immediately. It can only see one tree of height 5. Looking right, its view is not blocked. It can see 2 trees. Looking down, its view is blocked. Eventually, it can see 2 trees, one of height 3, and then the tree of height 5 that blocks its view. A tree's scenic score is found by multiplying, oh great, multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4, found by multiplying together 1 by 1, no wait, 1 by 1 by 2 by 2. However, you can do even better. Consider the tree of height 5 in the middle of the 4th row. Looking up, its view is blocked at 2 trees. Left 2, yeah. Okay, consider each tree on your map. What is the highest scenic score possible for any tree? Okay. So this is going to be more work than I had hoped for. Okay. So what do we have? We've got something that will mark the highest. That is of no use to us now. We've got some sort of a structure. We can go through all the rows. Can we go from a particular point on the map to the columns? Can we easily get going up, going right, going down, going left? No, we can't. Sort of. I mean, it'll be fine. Okay. And so we want to then get the number of trees it can see not just before the tallest one, because there could be a valley in the middle. There could be like a up, down, then really up. So we're kind of tracking the opposite really of what we did before. We're tracking not the highest, but any trees that are okay. I'm going to need to figure this out visually now. So let's go back to this. So let's say we pick this tree. We're currently at height. Actually, we have to take into account the height of the current tree, right? No, the tree. Look, to measure the viewing distance from a given tree, look up, down, left, and right from that tree. Stop if you reach an edge or the first tree that is the same height or taller than the tree under consideration. Okay. Okay. So let's say we picked this tree. We want to go and find, so this one is good. This one is good. So this would be a viewing distance of 1 if it's at the same height. So you count the tree you kind of get to. So this would be 2. And this would be 1. So it's 2 here and 1 here. Okay, so an algorithm for this is so it's really like we need to first get a list of trees in the given direction. For each tree in that list, let limit be the current, so the current tree's height. For each tree in that list, if the limit, if the tree's height is less than and or equal to limit. No, wait. Mark the tree visible. If the tree's height is equal to, is equal to limit, stop looping. Okay. So our 2 steps really So, okay, and then we get like, we actually don't want to mark the tree visible. We don't care if the tree is visible. We care, so we let count be 0, add 1 to count. Return count as viewing distance. So it's that sort of algorithm. So we need to have a function get view trees, which is going to be like for col and row. And a direction. Do we care about what direction it is necessarily? We just need 4. It doesn't really matter what direction they are. So it's like split the col on split the row on col, split the col on row. That would work. So if we've got like 1, 2, 3, 4, 5, 6, 7, 8, 9, and we take 5, which is at 1, 1, or col 1, row 1, given 0 indexing. Let me make that clearer. Well, I've just made it less clear, haven't I? Come on. So let's say we're at column 1, row 1, and we split the row on, we split the row 1 on the column, which is 1. We get rid of, we just get 4 and 6. And we split the row on the, yeah, that's good. Okay, that will work. And it makes use of our current data structure, which is good. Return 4 segments. Okay. And so we'll call this viewing calc, viewing distance. And then it's like this sort of thing. Okay. It's not code, honest. Okay, so we've got that. And then we need to go through every tree, which we can just do by going through all the cells. So that's quite easy. Loop through all cells, calc, viewing distance, and we want the best one, right? Highest scenic score. Oh yeah. Wait, no. Scenic score. Scenic score, scenic score. So we'll like store those anyway. Call row No, that's too much. Yeah, and then multiply, then it's like okay, so you get the idea. Great. Okay, I think we've got a plan. So in terms of plan of action, we're going to go with drive get view trees, drive calc viewing distances, 3, aim 4, I win. Okay. Note on efficiency, any efficiency things to worry about? We're going to go through all of the cells, and it's going to be essentially a column's worth per cell. Per cell, we're going to go through a column and a row. So it's going to be 20 operations per cell, and we've got 10,000. Yeah, we've got 10,000 cells, and we're going to have 20 operations per cell, I think. I think it'll be fine. Okay, right. So let me have this here. That's good. Get into Zen mode. And then we're going to base ourselves off of the previous code base. So I'm going to do that. I'm going to switch over to VS Code, do a bit of window management. Fight with Excalibur a bit. Okay, get rid of that and start the timer. I think we'll be okay with this one. Okay, so don't need this. Do need this. Don't need this. All these. And this is going to be different as well. So let me just get rid of that. Okay. And let's say we're taking an example. I want to take an example. See, I've just thrown away the thing I wanted. Why am I rewriting this? Why am I wasting my time? Okay. Okay, and we want to have this one. We want to go for why am I doing this nonsense? Anyway, Clearly too tired. Okay, structure, rows, col. So we want to split the row on the column. So let's say the column is 1, 0, 1, 2. Say col equals 2. Okay, perfect. Oh, wait. I want to split it on the row. Column, no, the column, the row, okay, row, split it on the column, and then if we do col minus 1, yeah, perfect. And then we want to have down, left to right, right to left. No, wait, no. This is us going left. And this is us going right. And actually, this one needs to be reversed. I should have spotted that. Okay. So let's say this was a column and we were line 3. And the row was 2. Then we want to get 2 and then 1 to go up. So we need to reverse that one. And then to go up. No, wait, that's up. Oh my gosh, okay. Come on. And that one's in the right order. So I don't need to reverse that. So left, right, up, down. Probably topple that up. Okay, so this is really distressing. So let's go with this structure. And one of the examples, which would be the middle 5 in the second row, which would be row 1, no, col 2, row 1. And that should equal, so going left, it should be 5, 2. Going right, it should be 1, 2. Going up, it should be 3. And going down, it should be 3, 5, 5. No, 3, 5, 3. And I've got a syntax error here for some reason. Oh. Okay. Puzzling. Oh, part 2. Okay, so that's wrong somehow. Okay, so it's right, it's the lemon 5, 2, 5, 2, 5, 1, 3, And then this one's wrong. Actually, I probably could don't need to reverse those, but we might need to optimize that if it gets slow. Okay, 3, 5, 3, 5. Okay. I don't need to do that right now. That's fine. I can just say that's right. And also is a tuple, so it's already not right. And it should be a list. I think it should be a list. Anyway, I'm getting tired now. So let me try it with a different one actually. So let me take row 0, 1, 2, 3, column, same column. At which point it should be 3, 3 to the left, which is right, 4, 5, 4, no, wait. Going right. It says 5, 4, but it should be. Okay, now I've gotten something wrong. 0, 1, 2, 3, 3, 3, 3, 3. So left is correct. Right is 5, 4, which is completely wrong. Down shouldn't be 3. Well, that's up actually. 3, 5, 3. That's right. And then 5. No, wait. 5 down is not right. That's not right. This one and this one is wrong. Okay, is the row right? 3, 3, 5, 4, 9. Yes, it is. So why is that not correct? 5, 4. From the because the column is wrong. Splitting the row on the column, and the column is 2. 0, 1, 2. Okay. 3, 3, 3, 5, 4, 9. Oops. Column is 2. 5, 4, 9. To minus 1, 5, 4. I swear that's not how that works. Okay. I totally had that piece of syntax wrong. That's a bit of a relief. Okay. I'll get rid of that. Okay. 3, 3, yes. 4, 5, 4, 9, wrong. Wrong. That needs to be +1, and this one needs to be +1. 4, 9, yes. 3, 5, 3, yes. 3, yes. Let's try it with the previous one again, because I'm not convinced by any of this. Okay, we're okay for time. Middle 5, second row. So row is 1, column is still 2. Okay, 5, 5, 2, yes. 1, 2, yes. 3, up, yes. 3, 5, 3, yes. Okay. Got myself muddled there. Okay, def. What are we doing? Calc viewing distances. Okay, let me comment that out. Don't need that. Hmm. Let the count be 0. For cell in view. If cell's height is, this would be easy to pass in the cell. Would be nicer. Okay, if cell height is greater than, oh no, wait. Candidate we don't change limit, so it doesn't actually have to be set at all. Okay, so if it's equal, if the tree's height is greater than or equal to the candidate's height, break count. Once we've got through this, distances append count, and then it would be assert count. Then distances is 4, and then return. No, wait, I'm not doing that yet. Although that's still a good assert. Okay. Right. And then this with okay, the row is 1, the column is 2. Fine. So we're going to calculate from there, and we want to say this should be 4. Okay, interesting. Come on. Obviously. Okay, that's good. And then for the one that's row 0, 1, 2, 3, column 2, this should be 8. Okay. Great. So next on the plan, the main pass. Want to get this. Great. Highest is -1 for cell in structure, all cells or all. Do we have product in Python? No. That would be too easy. Okay. Would there be a tie? Highest seen score possible is what we want. Eight. Is that good? Yes. Okay. Will it take 1,000,000 years to run? No. Thankfully not. 3, 2, 0, 1, 2, whatever it is. Let's put it in. Yes. 20 minutes on the dot. I did that in 20 minutes. Perfect. Okay. Well, not perfect, but I said I was going to do some more fiddling around to develop some sort of utility library. I'm not going to do that. I've got other stuff. I've got other things to spend my life on. They're supposed to be saving me time. She says 90 minutes later. All right. Good night.